Hey everyone, welcome to BK'sTechStack. Today, we're diving deep into the fascinating world of advanced generative AI, exploring the core models and architectures that make it all possible. Let's get started.
Before we get into the advanced stuff, let's quickly recap autoencoders. Basically, what's happening here is they're smart neural networks that learn to compress data into a condensed form, then rebuild it. Think of it like learning to summarize a book and then writing a new version from your summary. An autoencoder has three main components. First, the encoder takes your input and compresses it. That compressed data lives in the latent space, which is like the core summary. Then, the decoder tries to reconstruct the original input from that summary. It's all about learning a meaningful representation.
While traditional autoencoders are great for compression, they have some pretty big limitations, especially for generative tasks. They're not so good at creating truly new data, and they can often learn oversimplified representations. This means they struggle with the rich variability found in real-world data, which is where variational autoencoders come in.
Now, let's talk about variational autoencoders, or VAEs. These are like the advanced version of autoencoders because they bring generative capabilities to the table. Instead of just compressing, VAEs learn the probability distributions of your data, making them super powerful for generating new, realistic samples and capturing inherent data variability.
So, what makes a VAE different architecturally? While it still has an encoder and decoder, the encoder in a VAE outputs the parameters for a probability distribution, typically a Gaussian, not just a single point. This is crucial for its generative abilities, and it introduces a special KL divergence term into its loss function.
In a VAE, the encoder still compresses your input data. But here's the key thing you need to remember. It doesn't just give you a single compressed point. Instead, it gives you the mean and variance for a probability distribution, usually a Gaussian. Think of it as mapping your input to a fuzzy region in latent space, not a precise spot. The latent space in a VAE is a bit different. It's not just a compressed version of your data, it's a compressed probabilistic representation. Think of it as a smooth, continuous landscape where similar data points are close together, and you can sample from anywhere to generate new variations. This is vital for its generative capabilities. Once we have our probabilistic representation in the latent space, the decoder steps in. Its job is to take samples from that distribution and turn them back into something resembling the original input data. The quality of this reconstruction tells us how well the VAE is learning and ultimately how good its generated outputs will be. When training a VAE, we're trying to minimize a combined loss. The first part is the reconstruction loss. Basically, it measures how close the output generated by the decoder is to the original input. Think of it like a quality checker, making sure the VAE can faithfully reproduce the data it was given. This guides the VAE to capture essential features.
The other vital part of the VAE's loss function is the KL divergence. Now, you might be wondering why we need this. This term essentially measures how different the distribution learned in our latent space is from a simple known distribution, like a standard normal. It's super important for ensuring our latent space is smooth and well-behaved, preventing overfitting and enabling better generation.
Let's understand this step by step. First, you start with data collection, basically getting your training material ready. Then the encoding process happens, where your data is mapped to that probabilistic latent space. Next, we sample from that distribution, introducing some randomness. Finally, the decoder takes that sample and tries to reconstruct the original data or generate something new. The core of VAE training involves optimizing its objective function, which balances that reconstruction accuracy with the smooth latent space we talked about. This is achieved through backpropagation, where the model adjusts its internal parameters based on how far off its predictions are. It's a continuous cycle of refinement to make the VAE better at its job. Here's the exciting part, the generative capability of VAEs. Because of their continuous latent space, you can actually sample entirely new points and create novel data. Think of it like blending different ingredients to create a new flavor. This makes VAEs powerful for tasks like generating unique images or even synthesizing data for medical research. Beyond image generation, VAEs are super useful for things like anomaly detection, spotting the odd ones out in your data. They're also making waves in drug discovery, helping design new molecules, and are great for data imputation, filling in missing data points. However, a major drawback is that their outputs can sometimes be a bit blurry or less sharp. Now, if VAEs produce slightly blurry outputs, how do we get those super sharp, realistic images you often see? That's where generative adversarial networks, or GANs, come in. They use a brilliant adversarial approach with two networks battling it out, which leads to incredibly realistic and detailed outputs. The core of a GAN is its adversarial duo, the generator and the discriminator. Think of the generator as an artist trying to create the most convincing forgery. It takes random noise and turns it into something that looks like real data. The discriminator, on the other hand, is like a detective trying to spot the fakes. The training process for GANs is a fascinating zero-sum game. Initially, both networks start fresh. We first train the discriminator to be good at telling real from fake. Then we train the generator to fool the discriminator. This back and forth makes both networks better, pushing the generator to create increasingly realistic outputs until the discriminator can't tell the difference anymore. GANs are incredibly versatile. We see them in style transfer, turning ordinary photos into masterpieces. They're also amazing for image-to-image translation, like coloring old black and white photos or generating maps from satellite images. In the industry, they power virtual try-on experiences and even help create highly customized shopping recommendations. GANs offer some huge benefits, like unsupervised learning and their unmatched ability to produce high-quality, realistic outputs. However, they're not without challenges. They can be notoriously difficult to train because of that adversarial game. And watch out for mode collapse, which is when the generator gets lazy and only produces a narrow range of similar outputs instead of true diversity. That was a deep dive. Remember, VAEs for structured latent spaces, GANs for realistic images. Both are vital for AI's creative future. Keep building.